Hi everybody, hope you're having a great day. Today we're going to continue talking about acids and bases. We had a brief overview yesterday of acids and bases. We talked about some examples, the pH, that both give electrolytes in water. We talked about acids being sour, so they're in most foods, bases tasting bitter, so they're not really found in foods, but they're in a lot of cleaning supplies and so on. So we said that acids have a low pH, bases have a high pH, and neutral would be a pH of 7. And so we consider water to be amphoteric. Amph means both, like amphibian. And so water can both act as an acid and a base. So what exactly is an acid and a base? Well, there's different definitions. And so the first definition for acids and bases came along by savant Arrhenius. So he was an early chemist who was the first person to kind of distinguish between acids and bases or categorize them, substances as acids and bases. And so his definition said that an Arrhenius acid produces hydrogen ions, which are H+, or hydronium ions, which are H3O+, in water or in aqueous solutions. And that's consistent with the simple way that we think of acids. We think an acid starts with a hydrogen. And so what savant Arrhenius is saying is that when you put an acid in water, it produces an H+. So that hydrogen at the beginning of the formula is removed and comes off as H+, and then the rest of the formula is an anion. And so here we have both hydronium or H+, they mean the same thing, and they both, in reality actually don't really exist. So H+ doesn't exist by itself. In reality, it's surrounded by a bunch of water molecules, and so H3O+ kind of shows that. If you think about it, if you combine H2O and H+, you basically get H3O+. So that's what hydronium ion is. It's a hydrogen ion with water in it. In reality, hydronium ion doesn't even exist. In reality, it's really an H+ surrounded by like 6 waters. So, in reality, it should really be, like H13O6+, but that's a lot to write and think about. And so just to make it easier to think about, we either write H+ or H3O+. Again, we use them simultaneously. They mean the same thing. So an acid, according to Arrhenius, gives off this H+ in water. A base gives off a hydroxide ion in water. Remember, hydroxide ion is OH-. So that's also consistent with how we've been thinking about bases. To recognize a base, we've been saying that you look at the end of the formula, and if it has OH- in it, then that probably means that it's a base. So that is the simplest definition of an acid and a base. So let's look at an example here. So HCl, we normally would consider this an acid, and we think of it as an Arrhenius acid because when you put it in water, it gives off H+ and then Cl-. Or, you can also write it as H3O+ and Cl-. So as long as you see an H+ or an H3O+, that means it's an acid. A base is a substance that produces hydroxide ions in water. So for example, NaOH, sodium hydroxide, that's considered a base according to Arrhenius' definition, because when you put that in water, remember that's ionic, it's made up of ions, the water physically gets in between the ions to separate them, so you get Na+ and OH-. And so because you get hydroxide ions, that is considered a base. So we just looked at the very, very simplest definition of an acid and a base. But if you think about it, in class yesterday we talked about ammonia, for example, being a base, NH3. And ammonia doesn't have a hydroxide ion in it, so when you put it in water, it would not be a base according to the Arrhenius definition, but we know that it has basic properties. It's corrosive, it tastes bitter, it's slippery, all that stuff. And so we know that it's a base, but it does not fit the definition. And so there are lots of substances like that. And so we came up with a new definition of acids and bases, and that's the Bronsted-Lowry definition. So Bronsted and Lowry basically said that an acid is a proton donor and a base is a proton acceptor. So an acid is a proton donor, a base is a proton acceptor. So what is a proton exactly? A proton is basically an H plus ion. So again, H plus, so hydrogen ion, or H3O plus, which is hydronium ion, or proton, those are used interchangeably. They are the same thing. And we call an H plus a proton because if you remember, back in the first chapter or so, hydrogen, neutral hydrogen atom, has a proton and an electron. In order to become an H plus, it lost the electron, so all what's left is a proton. So basically, an H plus ion is just a proton, so that's why we call it that. So the definition for an acid is similar to the Arrhenius model. It's saying that it's a proton donor. That means it gives away an H plus in water, so that's similar. But the definition for a base is very different. Arrhenius said a base is something that gives off hydroxides, OH minuses in water. Bronsted-Lowry say that a base is a proton acceptor. It takes in that H plus that is given off by the acid. So let's look at some examples here. My arrows kind of are not showing, so let's rewrite them here. So if we look at this first example, HA is just kind of like a generic acid. It starts with a hydrogen, as always. B is our generic base. So when they react together, according to Bronsted-Lowry, HA is the acid, so it's a proton donor. So if it gives away an H plus, if that gives away an H plus, it then turns into A minus. After it loses an H plus, what's left would be an A minus. A base is a proton acceptor, and so that means it accepts or gains an H plus. So when it reacts, it gains an H plus. So if you add B with H plus, it becomes BH with a positive charge. And so we say that this is our acid and this is our base. Now, the Bronsted-Lowry definition or model, you have on one side of the reaction an acid and a base. On the other side of the reaction, you have a conjugate acid and a conjugate base. So the idea is that an acid has a conjugate base and a base has a conjugate acid. So let's look at that. So we have these pairs. So let's look at the acid. Here's my acid. It has a conjugate base. So an acid loses or gives away or donates a proton to become A minus. So we say that this is the acid and this would be its conjugate base. An acid and its conjugate base look the same, except that the acid portion has an extra H plus. So if you compare HA with A minus, they look the same, except the acid has an extra H plus. Now let's look at the base. So the base is B. It has a conjugate acid. So the base is a proton acceptor. It gains a proton. So when it gains a proton, it becomes BH plus. So then the base and its pair, you'd have a base and a conjugate acid. So the base and the conjugate acid look exactly the same, except the acid portion has an extra H plus. So whenever you have an acid or a base and its conjugate, they look exactly the same, except the acid portion has an extra H plus. Now, if you look at this side of the equation then, so let's say that this is a reversible reaction, which most reactions are. So if you look at this side then, so now this is that BH plus is the conjugate acid. This is my base or conjugate base. So according to the definition, an acid is a proton donor. So it gives away a proton. So when it gives away a proton in the reversible reaction, it turns into B. And A minus is my conjugate base. A base is a proton acceptor, so that means it gains a proton, it gains an H plus. When A minus gains an H plus, it turns into HA. So what if you have an acid in water? So let's look at the next example, HA and water. So HA would be our acid. Water, then remember, is amphoteric, so it can behave as either. So in this case, if it's reacting with an acid, then it must be a base. According to the Bronsted-Lowry definition, an acid is a proton donor. So it will donate, give away, an H plus. So what would be left? We would be left with A minus. And so an acid and its conjugate would be acid, and this one would be a conjugate base. Then we have water, which is a base. According to the Bronsted-Lowry definition, a base is a proton acceptor. That means it accepts the H plus that was given off by the acid. And so if H2O accepts an H plus, you'd add H2O and H plus, so you would get H3O plus. So this would be my conjugate acid. If you look at the reversible reaction, here's my base. So a base is a proton acceptor. So A minus accepts a proton to become HA. Let's look at my acid. Here's my acid on this side. And acid is a proton donor. So this gives away a proton. It donates it to become H2O. Now let's look at a base. So B is my base. If I put that in water, remember water is amphoteric, it can behave as either. So if you react it with a base, then this becomes my acid. So a base is a proton acceptor. That means it accepts a proton. So it becomes BH plus. And so if B was my base, BH plus would be my conjugate acid. And then H2O is my acid, and acid is a proton donor, so it gives away an H plus. So if H2O gave away an H plus, you'd get OH minus left, so that would be my conjugate base. Let's look at the reversible reaction. So on the other side, so here's my acid, and acid is a proton donor. If that gives away an H plus, it becomes B. Here's my conjugate base. So a base accepts a proton. So if this accepts an H plus, it becomes H2O. So just to recap, you have an acid with its conjugate base and a base and its conjugate acid. So the acid and its conjugate base are the same. They only differ in that the acid has an additional H plus. The base and its conjugate acid are the same. They only differ in that the conjugate acid has an extra H plus. So basically the acid portion has an extra H plus. So let's look at an example. We have HNO2 plus KOH yields KNO2 and H2O. So we want to identify where the acid is, where the base is, the conjugate acid, and the conjugate base for this reaction. So let's try. Looking at the reactant side, we know that we have an acid and a base. So there's several ways that you can recognize this. You know that HNO2 is your acid because it starts with an H. The other clue is that this has an OH, so you know for sure that that's a base. Now, according to Bronsted-Lowry, not all bases have an OH in them, but if they have an OH, hydroxide ion, that means it's a base. So that's pretty easy to figure out, I think, this side, that this is my acid, and then let's make that my base. Okay, now let's look at the other side of the equation. This one is really hard to figure out which one is the conjugate acid, which one's the conjugate base. So what you do is you look at the acid. Let's start with the acid. So an acid, according to Bronsted-Lowry, is a proton donor. It gives away an H plus. Now, if that gave away an H plus, what would you be left with? Well, you'd be left with NO2 minus. If you look at this side of the equation, there's no NO2 minus by itself, right? But where do you see a possibility of NO2 minus? Well, right here. What is this made up of? This is made up of K plus and NO2 minus combined, right? And so the K plus here is a spectator ion. It doesn't really do much in here. It just kind of swims around at the beginning, swims around at the end. So we call it a spectator ion. It's the NO2 minus that we care about. That is our conjugate base. And so an acid, when it loses a proton, it becomes a conjugate base. And so these two go together. And so I'm going to call this my conjugate base. An acid has a conjugate base. Now let's make, so that would make this one probably the conjugate acid, but let's make sure. So what you do is you look at your base then. A base is a proton acceptor, so it gains a proton. Now, if this gains a proton, what does it become? Well, if you have KOH and you add a H plus, you get KOH2 positive. Now, this is really hard to recognize, that this is the same thing as this, but it really is. This right here is basically my spectator ion, which is K plus, and then OH2, which is the same thing as H2O, basically. And so that is my conjugate acid because a base has a conjugate acid. So that one I think is really tricky. If you can do this one, you can probably do any of them. That's a pretty hard one. Moving on, there are different types of acids. We have monoprotic, we have diprotic, and triprotic acids. So let's look at the name here. Mono means one. Protic refers to a proton. So this means that it's an acid that can only give off one proton. So an example of that would be HCl, because HCl in water would give off H plus and Cl minus, so we only have one proton, so that would be monoprotic. Diprotic, di means two, protic means proton, so these are acids that can give off two protons. For an example, that would be like H2SO4. And in reality, it gives it off on multiple steps. So basically, H2SO4 gives off an H plus, and then you'd have HSO4 minus left. But then HSO4 minus can give off an H plus and SO4 2 minus. So the total at the end is basically two protons. Here's one, and then here's the second one. Triprotic would mean that it gives three protons. Tri means three. So an example of that would be like that would be three protons. So an example would be H3PO4. So again, it does it on multiple steps. So H3PO4 can give off an H plus and H2PO4 minus. Then H2PO4 minus can give off a proton and HPO4 2 minus. And then finally, HPO4 2 minus can give off a proton and PO4 3 minus. So if you add them all up together, there's one proton, there's the second one, and there's the third one. Let's practice some more of the conjugates. So this question is asking you to identify the conjugate base for each of the following. If I want the conjugate base, that means that these are acids. So these already have the extra H plus. And so if I want the conjugate base, basically I remove an H plus from them. So again, if I want the conjugate base, that means these are already acids, so they already have the extra H plus, so I remove the H plus from them. So let's do the first one. HCl, if I remove an H plus from HCl, I'd be left with Cl minus. Now watch out that you put the charge there. It's not neutral Cl, but it's Cl minus because HCl is neutral, so if you remove an H plus, you remove a positive, so you'd be left with a negative. Next one, H2SO4. So you're going to remove one H plus from it, only one, so you'd be left with one hydrogen and then SO4, and a charge of negative, because it was neutral and you lost a positive, so you'd be negative. Next one, H3PO4. So you remove one H plus. So that means you'd be left with H2PO4, and then again a negative. Let's look at the next one, HPO4 negative or HPO4 minus. So you're going to remove one H plus, so you'd be left with HPO4, and then you were a negative 1 charge, you removed a positive, so now it would be 2 negative. The last one, HPO4 2 minus, you're going to remove an H plus from it, so you'd be left with no hydrogens, you'd be left with PO4, and then you were 2 minus, you removed a plus, and so total is 3 minus. Okay, the next set, you want to identify the conjugate acid. So if you want the conjugate acid, that means these are the bases. So if you want the acid, it would have an extra H plus. So now we are doing the opposite. We're adding an H plus. So NH3 with an H plus would be N, and then instead of 3 H's, we're adding an extra H plus, so now it would have 4 H's, and it was neutral. We added a positive because we're adding H plus, so the total would be positive 1, so NH4 plus. Next one, HCO3 minus. So again, we're adding an H plus, so now we'd have 2 hydrogens, so H2CO3, and we were negative. We're gaining a positive, so negative and positive become neutral, so H2CO3. Next one is OH minus. We're adding an H plus, so it becomes OH2. It was negative, we add a positive to it, so it becomes neutral. So OH2, or basically H2O, same thing. Next one, HPO4 2 minus. So we're adding an extra H plus to it, so it becomes H2PO4. It was negative 2, we add a positive, so the total is negative 1, so H2PO4 minus. Be careful, this is one of the number 1 mistakes on the test, is people switch these up. So remember, if you're finding the base, a base has one less H plus, so you remove an H plus if you want the base. If you want the acid, an acid has an extra H plus, so you add an extra H plus if you want the acid. So be careful not to mix these up. One last thing here, the stronger the acid base, the weaker the conjugate. So if you have a really strong acid, its conjugate base is going to be very weak. And the weaker the acid base, the stronger the conjugate. So if you have a very weak acid, its conjugate base will be very strong. So they're kind of opposite of each other. Okay, these are not in your notes. I just wrote them up real quick just to practice the acid-base conjugate, acid-conjugate base. So let's do that real quick. So the first example, we want to identify the acid, the base, and the conjugate, acid-conjugate base. So in this one, we have HCl and we have water. Remember, water could be amphoteric, so you want to look at the other one then. This starts with an H, and we know that hydrochloric acid obviously is an acid. So this side is easy. We can tell that this is the acid, and then this is the base. So then let's look at the other side. So HCl is an acid according to Bronsted Lowry. It gives away an H plus. So if this gave away an H plus, it becomes Cl minus. So those two basically go together. So this would be the acid, so then Cl minus would be the conjugate base. Let's double check with the other one. So H2O is my base. A base accepts a proton. So if H2O accepts or gains a proton, basically it becomes H3O plus. There it is. So these two go together. So if that was the base, this is my conjugate acid. Let's look at the next one. KOH and H2O. Again, H2O is amphoteric. So let's look at KOH. We know potassium hydroxide is a base. If you're not sure, you know that it ends with hydroxide, so that's probably going to be a base. So We know that this is our base and this is our acid in this case. So let's look at the base first. KOH is the base. It accepts a proton. So if it accepted a proton, it becomes KOH2 plus. And so these two go together. So if KOH is my base, then this is my conjugate acid. H2O was my acid, and acid is a proton donor, gives away a proton. So if this gave away an H plus, you'd be left with OH minus. So these two go together. If H2O is the acid, then this would be my conjugate base. Okay, last one's a little bit more difficult. We have HF and LiOH. So HF, you can probably tell that that's an acid because it starts with H. And LiOH, you probably can tell that that's a base because it ends with hydroxide. But then the other side is a little bit more difficult. So let's start with HF. HF is an acid, so it donates a proton, gives away a proton. So if that gave away a proton, you'd be left with F minus. Now there's no F minuses by themselves on the product side, but this one is basically Li plus and F minus. So remember, like the last problem, the Li plus is just there holding the charge, it's just holding a spot. It's a spectator ion. So there's the F minus there. So these two go together. If HF is the acid, then that must mean that this is the conjugate base. Let's look at LiOH. So LiOH is my base. A base is a proton acceptor. That means it gains a proton. And so if this gained a proton, it becomes LiOH2 with a positive charge. Now we don't see that on the other side, but this is the same thing as Li plus and water. And remember, Li plus was a spectator, and so really it's the water that we care about. So these two go together. If this was my base, then this is my conjugate acid. All right. Hope you guys have a wonderful rest of your day, and we'll continue with the notes tomorrow.